In this presentation, you will learn about logarithms with bases other than 10 and the natural logarithm, or simply stated, ln of x. And I should remind that there was a separate presentation on logarithms where we studied specifically logs to base 10. So this is a continuation of that topic. So in the previous segments, we've seen the log function simply to base 10, and we learned that when you write just log of x, that's understood to be base 10. And we've seen important properties of log functions to the base 10, such as when we write log base 10 of 10 to the fourth, we saw that was just 4. Also, if we write log of x equals to 2, then to solve for x, what we have to do is write down 10 to the second power. Again, the hidden base is 10, so 10 to the second power equals x. And we also saw the property of logs where we have log of x to the power r equals r times log of x. That means r that was as an exponent of x previously can be brought in front of the log function as a coefficient. Again, a unique property of logarithmic functions. And at the end of our first segment on logarithms, we looked at some applications of log functions, such as pH calculations, created graphs using logarithmic scale that gave us more clarity, and we solved equations where the unknown was in the exponent. But logarithms are not restricted to just base 10, even though we may have given that impression in our previous presentations for simplicity. It's really possible to have logarithms to any base, as long as the base a is a number greater than 0. So for example, logarithm to the base 2 of 16 equals 4, because 16 can be written as 2 to the 4. So just like when we studied base 10, as long as you can write a number to the same base as the base of the log, the given logarithm will only record the power, or the exponent. So if we're dealing with log base 2, so we try to write 16 with a base 2, which is 2 to the 4th. And therefore, as long as the base 2 here and the base 2 here are matching, the logarithm will give us just the exponent, or 4. Similarly, log base 3 of 9 is 2, because 9 can be written as 3 to the power of 2. And one more example, log base 5 of 125 is 3, because 125 can be written as 5 to the power of 3. So as long as you can write this number with the same base as stated down here, then the exponent of that base will be the answer to your logarithm. And more generally, we can state that log base a of x is equal to p if and only if x equals a to the power of p. And if you think backwards, take this a to the p, put it back in there, you will see that you will be getting just p, the exponent, or the power. And this brings us to the most famous base of all times. Okay, maybe slight exaggeration, but nonetheless a very commonly used base is base e, which represents Euler's number 2.7182818 and so forth, a non-repeating decimal. And this comes up so often with logarithmic functions that it has a special name. Logarithms to the special base is represented by simply ln, short for natural log. So if we write ln x, what that means is logarithm of x, but to the base of e. And all the properties of logs that we've learned previously apply to natural log function instance. Natural log of e to the 4th will be just 4, because the hidden base is e, so this is like log base e of e to the 4. Therefore, since this base matches that base, we just report the power, which is 4. More generally, we can write ln of e to the r, where r is any number, is going to be equal to simply r. And what about something like ln 25? We don't know 25 as e to a power, and therefore this would be a good situation to use a calculator. So at this point, just go to your calculator and you will see that there is an ln key in there and a log key, because those are the two most commonly used bases, base E or base 10. In this situation, just press ln 25, press enter, and you should see the answer emerging as 3.22. And here is another question going backwards. If we have ln of a number equals to 2, then can you guess what x will be? So what would you write here so that the answer turns out to be 2? It has to be e to something, right? And that answer is e to the power of 2. And let's take a look at a few more examples involving logs. This time we're going to solve exponential equations. Each of the question will ask you to solve for x. Let's start with e to the x equals 25. As we have seen previously, anytime the unknown x or something that involves the variable appears in the exponent, it's a perfect situation to bring in the logarithmic functions to solve for that unknown. In this situation, we're going to stick with the natural log function, but just know that technically you can use log with any base. Again, the easiest one would be natural log in this situation since we're dealing with base e. Apply ln to both sides. Simplify the right-hand side and simplify the left-hand side. We've learned ln of e to a power will be just that power, and the right-hand side ln 25, as we've seen, can be simplified as such. Here's another example. 3 to the x equals 100. Yes, of course, we could do a trial and error here. You know, you could try 3 to the 4, 3 to the 5, and so forth to see where, which number is closest and go from there. But it's so much easier to use logarithmic functions. All you have to do is apply natural log to both sides and simplify the left-hand side as x times ln 3. Remember one of those properties we've reviewed earlier. And now to solve for x, since these are being multiplied, x times ln 3, to get rid of the ln 3, divide both sides by ln of 3, and you will have the answer. The important thing though, when you're entering this in the calculator, make sure you close the parenthesis for ln 100 before you press the division sign. And one more example. 5 times 2 to the x equals 25. Solve for x. Now you're probably saying, okay, sure, let's apply ln to both sides, but not so fast, because this 5 on the left-hand side first should be gotten rid of, because to apply natural log and to be able to bring the power x, you need to isolate the exponential term first. So divide both sides by 5 to begin with and to isolate the exponential expression. So divide this side by 5, this side by 5, they're going to cancel, and 25 over 5 is 5. Now we have what looks like more like a standard form for an exponential equation, and then apply natural log to both sides, and the rest should be pretty straightforward. Bring down the x using the property of logs and divide both sides by ln of 2. And here are some reminders about additional properties of logs, which we've already seen with base 10. So for example, ln of x times y equals ln x plus ln y. Also known as logarithm of a product is the sum of the logarithms, and this could be stated with log to any base. Here I'm just using base e since we're just emphasizing that one. Similarly, logarithm of a quotient equals difference of the logarithms, but be careful about the signs. The one that is positive should be the one that is on the top. So ln x minus ln y. And also quotient, please note that we cannot simplify the following. Ln of x plus y or ln x minus y. We cannot just distribute the natural log function. Such a property does not exist. So to take a look at an example, let's simplify the given expression. And the plan is going to be as follows. First of all, I see ln of a quotient. So let's use the subtraction rules. Ln of the top minus ln of the bottom. Then I see a product. We can further simplify it by writing as the sum of two logarithms. And finally, each of these exponents can be brought down to simplify this further. So that would be the simplest way to write that expression as a sum or difference of logs. And if you're wondering why we would, why in the world somebody would want to write this in that format, well, some of you may take calculus and you might see that if you're going to apply, for example, the derivative to a function like this, it is so much easier to simplify it first and then be able to take the derivative. And please stay tuned for the next segment, titled Logs Part 3C, where you will see an application of logs involving radioactive decay and half-life.